Alright, so I will be presenting 6.3.1 desirable bandwidth allocation. So what is desirable bandwidth allocation? Bandwidth allocation is run by a congestion control algorithm, and the goal of it is to avoid congestion and in addition find a good allocation of the bandwidth to transfer data. A good allocation will deliver good performance due to the fact that it uses all the bandwidth and also prevents congestion. Sorry. A good allocation delivers good performance, uses all the bandwidth because it avoids congestion, and this leads to um, efficiency and the power of desirable bandwidth allocation. As you can see in A, there's an x-axis of the offered load, which is in packets per second, and the good put, which is also in packets per second, and the desired response is in between the congestion collapse and the up until the capacity, and that's like the sweet spot for what you want. And B is a delay as a function of offered load, and as you can see, there is an x and y axis of offered load and delay, and it's an exponential curve where the gray circle is seen as the onset of the congestion. And the good put, good reason you should remember the good put is that it's the rate of useful packets that arrives at the receiver as a function of the offered load. In figure A, as the load increases, the good put increases initially, but as it approaches the capacity, the good put also rises, and the fall off where the congestion collapses is due to bursts of traffic that can mount up and cause losses in the network. And the power formula for the network is power equals load over delay. So this means that performance begins to degrade at the onset of congestion, and we will get the best performance from the network if we allocate the bandwidth up until the delay begins to climb rapidly. And you want the point is going to be below the capacity. Power will rise initially with offered load as the delay remains small and constant, but it'll reach a max and fall as the delay grows rapidly. And the load with the highest power represents an efficient load for the transport to place on the network. And next we have max-min fairness, and this means that an allocation is max-min fair if the bandwidth given to one flow cannot be increased without decreasing the bandwidth given to another flow with an allocation that's no larger. And this is to say that increasing the bandwidth of a flow only makes the situation worse for flows that are less well off. And as you can see in this figure, this is the max-min bandwidth allocation for 4 flows. And a good way to think of this is to imagine the rate of all the flows start at 0 and increases slowly, and once it reaches the bottleneck, the flow stops increasing, and all the other flows continue to increase and share equally in the available capacity until they also bottleneck. And another concept of bandwidth allocation is convergence, as you can see with time on the x-axis and bandwidth allocation on the y-axis. And as you can see that this is an example of a bandwidth allocation that changes over time. And initially flow 1 has all the bandwidth, and then 1 second later flow 2 starts, which also needs bandwidth, and the allocation changes to give each of the flows half the bandwidth, and at 4 seconds a third flow is joined, and which only uses 20% of the bandwidth, and flows 1 and 2 adjust for that, and at 9 seconds the second flow leaves and the third stays the same, and the first flow returns to 80% of the bandwidth, and at all times the total allocated bandwidth is close to 100%, so that the network is fully utilized and different flows get equal treatment.